Chapter 10, Energy, Part 2, Potential Energy. Okay, so we just talked about kinetic energy. Now we're going to talk about potential energy, and there's a few different types of potential energy that we'll talk through. First, let's talk about gravitational potential energy. So gravitational potential energy, U sub g, is equal to the mass times the acceleration due to gravity on the Earth, that's 9.8 meters per second squared, times the vertical height, which we're representing as the y coordinate. Mgy, the vertical height, gives me the gravitational potential energy. The change of gravitational potential energy is equal to the mass times the acceleration due to gravity times the change of height. You could also say that's the gravitational at the end minus the gravitational at the beginning, but I could just do change of y. Now for kinetic, I had to separate those out, but because this isn't squared, I can just do the change of y and it'll be the same. All right, so stop and think. Rank in order from largest to smallest the gravitational potential energy of these identical balls 1 through 4. Let's see, if they're identical and they're all on the Earth, then they all have the same acceleration due to gravity. They all have the same mass. The only thing that's changing is the height. Does velocity matter for gravitational potential energy? It does not. So I can just ignore all those green lines. Those don't matter. So the only thing that matters is the height. Which one's the highest? That would be 3. So ranking in largest to smallest, 3 is the largest. That's going to be more than the next highest ones, which are 2 and 4. 2 and 4. And those are going to be more than the smallest one, which is 1. That has the lowest gravitational potential energy because it's all based on height. All right. With that in mind, it's all based on height. It also means that the path that you take doesn't matter. As long as you start in the same location and end up in the same location height-wise, how you get there doesn't make a difference. So we got a couple examples for these hikers. This hiker goes up a steep route and then a flat route and then a gentle route to end up at the top. The second hiker goes on a gradually increasing route, steep, and then ends up at the top. They both started down at the bottom. They both ended up at 200 meters. So they both have the same change of gravitational potential energy, assuming no friction, right? Assuming that the friction doesn't matter. As long as you start at the beginning, end at the end, the change of gravitational potential energy is the same. All right, let's talk about another type of potential energy. The second type of potential energy we're going to talk about is spring potential energy. This can also be called elastic potential energy. It's the potential energy held in a spring or elastic surface. I'm going to use a rubber band as an example, but anything that can compress and expand could have some elastic potential energy. Even a piece of plastic, right? If it can expand and contract, even microscopically, there could be some spring potential energy by squeezing it and then having it push back out. The equation for spring potential energy is 1/2 kx squared. So x is pretty obvious. That's the change of distance or change of displacement. K is the spring constant. So K is a spring constant, and you can find the spring constant using something called Hooke's law. So Hooke's law states that the force exerted on a spring is equal to the spring constant times the distance that the spring compresses or expands due to that force. We can also say that's F equals Kx. So if I have a spring like this, I could hold it vertically without stretching it, right? There it is. Then I could exert a constant force on it, maybe by hanging a weight from it or using a spring scale and hanging it there. And I could see how much does it end up stretching. So I would measure from where it started from, that far, to where it ends up, that far. Say that's a change right here of 10 centimeters of stretching. Then my X becomes 10 centimeters. The force I exerted, let's say I hung a 500 gram mass on there. So that's a force of 4.9 newtons. So 4.9 equals K times 0.1 meters. Divide both sides by 0.1, and that would give me a K of 49 newtons per meter, right? So 49 newtons per meter could be the spring potential energy, or sorry, the spring constant of this rubber band. And 49 newtons per meter is a reasonable spring constant for something like a rubber band. Okay, then I could take that spring constant, plug it back into this spring potential energy, and then say, okay, well, what if I pulled the rubber band 15 centimeters instead of just 10? Well, then I could put in 15 centimeters in here and solve for my spring potential energy. Great. So let's do that by looking at pulling back on a bow. And a bow is a springy surface. It's a kind of flattish piece of wood or plastic, and then it bends and holds potential energy, and then it expands again. An archer pulls back the string on her bow to a distance of 70 centimeters from its equilibrium position. To hold the string at this position takes a force of 140 newtons. How much elastic potential energy is stored in the bow? Okay. So pulls back the string. Let me draw this one out. So we've got my bow here. There's my string. The string gets pulled back a total distance of 70 centimeters. So that's 0.7 meters. And that takes a force of 140 newtons. Okay. So force is equal to Kx. 140 newtons is equal to the spring constant times x, which is 70 centimeters, 0.7 meters. So then my spring constant is 140 divided by 0.7, 200 newtons per meter. Okay, so that's my spring constant. Now I can plug into the spring potential energy, because that's what's asked for, the elastic potential energy, equals 1/2 kx squared. U sub s equals 1/2 times k, which was 200 newtons per meter, times x squared. X in this case is the same that she was pulling back, right? In this case, it's the same x. I don't have to modify it at all. So that's 0.7 meters squared. 0.7 squared is 0.49 times half of 200 is 100. So the spring potential energy is 0.49 times 100, or 49 joules. Great. So how much spring potential energy is stored in the bow? 49 joules of potential energy. And you'll notice in this case, the bow has a much higher spring constant, 200 newtons per meter, than I said my rubber band does. My rubber band only had 49, which was 50, so the bow would have 4 times more potential energy, which makes sense. Bow is much more significant than this little rubber band. Nice. All right, let's do a stop and think. When a spring is stretched by 5 centimeters, its elastic potential energy is 1 joule. What will its elastic potential energy be if it is compressed by 10 centimeters? Okay, so stretched by 5 versus compressed by 10. So first, stretched and compressed are just different directions from equilibrium, right? If I say my spring is normally this, stretched by 5 is 5 off equilibrium, compressed by 10 is 10 off equilibrium. Both ways, it's a change from equilibrium, so I can use the same spring constant. It's the same spring. The same spring should have the same spring constant no matter what, as long as you don't like break the spring, or stretch it out or whatever. Turns out in real life, you can modify the spring constant by using it a whole bunch, where it gets damage on it. Like if you use the rubber band over and over again, the rubber band will get stretched out and then its spring constant will change. But for our purposes, we're going to assume springs maintain the same spring constant. So 5 centimeters versus 10 centimeters. And at 5, it was 1 joule. So I'm going to use U sub s is 1/2 kx squared. So the k is going to stay the same, right? That's constant. Half is a constant. It started with 1 joule, right? Was proportional to x squared, 5 squared. And now if I go 10, so 10 is twice 5. So that went times 2. So times 2 squared would be 4 times more potential energy. So I should end up with 4 joules of potential energy because it doesn't matter if it's positive or negative, right? Because it's squared. And since I'm squaring, the negative and the positive don't make a difference. So I should be D 4 joules, right? Because even if it's a negative number, okay, it's negative 10 squared, that's still a positive. 2 negatives do make a positive in math or physics. Unless you're adding them, then they don't. So morality still holds? Yeah. Okay. Thermal energy. For thermal energy is due to friction. And because thermal energy is due to friction, we can say thermal energy is the work done by the force of friction, right? So the change of thermal energy would be equal to the force of kinetic friction, it's the force of moving friction, times the distance that was moved, right? Or thermal energy is the kinetic friction force times the change of distance. Because remember, work is force times distance. So that equation would hold. Let's talk a little bit about why that happens. Like, why does that make any sense? So thermal energy is basically looking at molecular kinetic energy and spring potential energy. So in a hot object, molecules move really fast. So if I have something that's heated up, when it's heated up, the molecules are vibrating, and they're vibrating real fast. It might be a solid, so they might still be like stuck together. They're not moving relationally to each other, but in their positions, the reason that it's getting hot is that their molecules are moving. As they move, the bonds between them, like these guys right here, are getting compressed and expanded. So I have both the kinetic energy, which is these green arrows, right? That's getting big, and the spring potential energy of the bonds, which is a weird way of thinking of bonds, but you could think of bonds between atoms as having spring potential energy holding them in place. So those spring potential energies are also compressing and expanding. So if something's really hot and its molecules move faster, it has more kinetic energy at the molecular level, more spring potential energy at the molecular level. So hot objects have lots of thermal energy, kinetic and spring, because they have faster molecules. Cold objects, like this ice, their molecules are going to move a lot slower. The molecules are still moving, but they're vibrating in a much smaller location and they're going slower. So their arrows are smaller, and as a result, their springs, their bonds aren't springing as much. They're just kind of like that. They're chilling. Chilling. See what I did there? It's a pun. It's a good one. So there's less movement because of the smaller molecules, slower molecules. All right, so how does that work? How does friction lead to these faster or slower moving molecules? Well, we've already said that at the interface of two objects moving past each other, there are these kind of jagged sections. And I think it was like 1/10,000th of the points would actually hit. But at those points that do hit, the molecules are going to bond to each other and then break those bonds and spring back. So the spring-like molecular bonds stretch, store elastic potential energy, and then break, and then it has to be converted into kinetic and potential energy of the atoms, which is thermal energy. So at the physics level, we're not thinking so much about the molecules. We're just measuring it as heat coming off of those molecules. But really, it's the movement of those molecules, forming bonds, breaking bonds, boing, kinetic, spring, gives me thermal on the molecules level. So as I go past, I'm connecting, breaking, springing to give me that thermal energy. For our purpose, though, I could just say force of kinetic energy times the change of distance, and that'll give me my thermal. And remember, kinetic energy force is equal to the normal force times the coefficient of friction. All right. So a block with an initial kinetic energy of 4 joules comes to rest after sliding 1 meter. How far would the block slide if it had 8 joules of initial kinetic energy? Okay. So I am balancing my kinetic with my thermal, right? Because it's the friction that's slowing it down. So in this case, I have let's use a different color. My kinetic energy is turning into my thermal energy. My kinetic energy has doubled. So I've gotten from 4 to 8 in terms of kinetic. So that's a times 2. The thermal energy is equal to the force of kinetic friction times the change of x. The force of kinetic friction is equal to the normal force times the coefficient of friction. So that would be normal times mu sub k. That should be controlled by the object, so that doesn't change. Normal force is based off of the weight of the object, so that doesn't change. So if I double the kinetic energy, I should double the distance that's traveled, because that is kinetic to force of friction times the change of x. But I know that the force of friction is going to stay the same based off of the normal and the coefficient of friction. So whatever change I do there times 2, I should do to the change of distance times 2. So it was 1 meter times 2 gives me 2 meters B. All right, metacognition. Here we go. So let's do another example for force of friction, creating thermal energy by rubbing. A 0.3 kilogram block of wood is rubbed back and forth against a wood table 30 times in each direction. The block is moved 8 centimeters during each stroke and pressed against the table with a force of 22 newtons. How much thermal energy is created in this process? Okay, so I am looking for how much thermal energy, so that would be E thermal equals the force of kinetic energy, kinetic friction, sorry, times the change of distance. Okay, and then I know that the force of kinetic friction is equal to the normal force times mu sub k. Okay, so the normal force is given up here as 22 newtons, right? That's the force that I'm pressing against the table, and that's equal to the force that the table is pressing back against the block. Or do I need to account for the weight of the block too? Is it going to have to be the weight plus the force? It might be. Ooh, I'm going to double check on this one because I think I might have to also include the weight. And indeed I do. Okay, so that is not totally the normal force. I'm glad that I paid attention to that. Okay, so step one is let's figure out the force of the block. So I'm actually going to draw a force diagram on this one. It'll be fun. So pushing down, I have the weight of the block. And then I've also got on the block the force of the push, right? The force of the hand down on. Okay, and those are going to balance out to equal the normal force. So the weight is equal to mg, which is equal to 0.3 kilograms times 9.8 meters per second squared. Got that fun motion sensor light going on, which is equal to 0.3 times 9.8, 2.94. 2.94 newtons. The force of the hand is 22 newtons. So if I add those together, 22 plus 2.94, that gives me the normal force has to be equal to 24.94 newtons, or pretty much 25 newtons. I'm going to effectively round that to 25, but we'll keep it there for now. Okay, the coefficient of friction, I have to look up because it's a block of wood rubbing against a wood table. So that would be wood on wood, and I'm pretty sure that that is a coefficient of friction of 0.3. But let me double check. It is 0.2. Okay, so the coefficient of friction for wood on wood, U sub k, for wood on wood is 0.20. Okay. And that was in chapter 5, I believe. There was a little table in chapter 5. I'll see if I can find the page number. Chapter 5, coefficients of friction. There they are. Page 138. Right there. All right. So 0.20 was the kinetic friction for wood on wood. So now I could say that that force of kinetic friction is 0.2, 0.20 times my normal force, 24.94 newtons, which equals 24.94 times 0.2, 4.988. So that's pretty much 5 newtons. All right, so pretty much 5 newtons there. Then the total displacement, how much did I move it? So it was 30 times in each direction. So the 30 times in each direction makes me think it's 30 this way and then 30 that way. So 30 and 30 is going to end up giving me a grand total of 60 back and forths, right? 30 this way, 30 this way. So for my delta x, that was 60 motions, and each one was 8 centimeters, 0.08 meters. 60 times 0.08, 6 times 8 is 48, 4.8 meters total. So now the thermal energy is equal to 4.988 newtons times my distance, 4.8 meters, for a grand total of 23.9, or rounding it to 24 joules of thermal energy. Nice. All right, I feel pretty good about that one. Sweet. All right, so let's keep cranking, and we will talk a little bit about conservation of energy. So conservation of energy is the idea that energy is neither created nor destroyed, but is transferred between forms. So what this means is that in an isolated system, remember this is assuming we can keep everything within the same system, the total energy at the beginning, or the sum of all energies initial, is equal to the sum of all energies at the end, right? So the beginning has to be equal to the end. Now, if I add up all the energies that we've been talking about, that would be kinetic at the beginning plus gravitational potential at the beginning plus spring potential at the beginning plus any work that I put in is equal to the kinetic at the end plus the gravitational at the end plus the spring at the end plus any change due to thermal energy, so any heat lost. So basically, this is just separating it down the middle and saying the beginning part has to be equal to the end part. Set them all equal. Now, some of those are going to be zeros, right? Some at the beginning or some at the end will be zeros. So just pays attention to what did I start with, what did I end up with, and then make them equal. And that's the conservation of energy. So let's try that. Back up to the top. Here we go. So at the county fair, Katie tries her hand at the ring the bell attraction, as shown in figure 10.2. Didn't copy that one. She swings the mallet hard enough to give the ball an initial upward speed of 8 meters per second. Will the ball ring the bell 3 meters from the bottom? 3 meters up. The bell is 3 meters above where the ball leaves. Okay. So I could do this with a change of energy, right? Energy at the beginning equals energy at the end. At the beginning, the energy that the ball has is kinetic. So I would say kinetic initial is going to turn into the ball at the very top is going to have potential. Oops, not P, U sub G at the end. So if I plug those in, 1/2 mv squared equals at the end UGF mg, and that is the change of height, y. Okay, so I've got mass on both sides. Those masses will cancel. V squared is going to be 8 meters per second. 1/2 times 8 meters per second squared equals gy, 9.8 meters per second squared times the height. So 3 meters is how high up the bell is, but I want to figure out how high the ball would go if the bell doesn't get in the way. So I'm just going to say y is my height. 1/2 of 8 squared. 8 squared is 64. 1/2 of that is 32 meters squared per second squared. Divide by 9.8 meters per second squared. 32 divided by 9.8 gives me 3.27. 27 meters equals y. So the ball could go up to a height of 3.27 meters. The bell is 3 meters from the bottom. So yes, the bell will ring. Is there another way that we could do that? Well, this one, it turns out we could also just use our motion equations, our kinematic equations. You might remember that equation. V sub y squared equals v sub y 0 squared plus 2a change of y. In this case, I'll solve for change of y. V sub y is my final, that's at 0, right? It goes all the way up to the top and stops. So 0 squared equals 8 squared plus 2 times 9.8 change of y. negative 9.8, the acceleration is downwards. So negative 64 equals negative 19.6. Change of y, solve for change of y, equals 3.27 meters. Checks out. Yep, same answer. So I could use either one, energy or kinematics. So let's use one where we actually have to use some energy transfers then. So this one, I can't just use kinematics because now I'm going to have some spring potential energy. And we're going to solve that one at the beginning of part 3 because I have to start live class now. So we will pick this up in just a second for you, but in 3.5 hours or so for me.